Hello, welcome to today's webinar on precision fluid measurement and advanced node fabs. This is Pete Singer, editor of Semiconductor Digest and today's moderator. Thank you for joining us. So we have a great presenter today, Jay Rajagopalan, and he is the Senior Director of Engineering and Product Management at Malima. And he has 35 years of experience in engineering, sales, and product management. So very experienced. And we will have a question and answer session after Jay's presentation. You can ask a question then, of course, or really at any time during the presentation, and we'll get to those during the Q&A. And it's pretty easy to ask a question. Just use the chat function on the right-hand side of your screen. And you'll also see that there's a download. You can download a copy of the presentation in PDF form. So with that, please welcome Jay.
Yeah, thank you. Thank you very much, Pete. And thank you all for joining this session. Pete, thank you very much for hosting us and also giving us a chance to present this very important topic, which is precision fluid flow measurement in advanced node fabs. We are going to focus in this discussion primarily on CMP, wet processing, and point of use control challenges. And as Pete mentioned, I'm Jay Rajagopalan. I'm the Senior Director for Engineering and Product Management at Malima. Before going into the presentation in detail, I would like to touch upon Malima, introduce Malima to folks who have not known Malima, but many of you would have already have experienced Malima products. Malima at a glance. So Malima is a 45-year-old company that focuses on precision flow measurement and control products, design and manufacturing of these products for demanding applications such as slurries, surfactants, high purity corrosive chemistries, etc., used in semiconductor industry as well as life sciences industry. We make widest range of flow technologies, stretching from ultrasonic Coriolis, vortex, paddle wheel, flow meters, as well as flow controllers. The company itself was founded in 1981 in Florida. Since then, July of 2022, we are acquired by PSG Dover. Dover is an industrial conglomerate spanning across various industries. There are $8 billion company with over 25,000 employees worldwide. Malima specifically operates out of 3 manufacturing sites, 2 in the US, 1 in California, and 1 in Florida, and in India. We have a very strong R&D program. We introduced a lot of new products to the industry as well as to the world in the high purity segment. All our manufacturing facilities do have Class 6 clean room manufacturing. Malima evolved over these years. It started in 1980s as a humble beginning with the flow switch product used in industrial applications, as well as excess flow valves, which are used to shut the flow off if the fluid line were rupturing and causing environmental or catastrophic damages. From that beginning, in 1990s, we gotten into the semiconductor industry. We introduced several high purity flow switches, flow meters in the 90s. Get our feet wetted into that industry, so to speak. And 2000 onwards, for the next 2 decades, we embarked on developing a lot of new technologies to the industry, be it first straight tube ultrasonic flow meter, or first integral ultrasonic flow controllers for the industry, as well as the world's first PFA or peak Coriolis flow meters and flow controllers for both high purity markets that we cater to. In 2020s, of course, we got acquired by PSG Dover, and semicon obviously is exploding, market is expanding. So we are expanding our production facility 3 times the capacity that we currently have. And our products also, I mean, as you know, that 2020s, we got into COVID situation. We introduced world's first single-use Coriolis mass flow meter for use in the COVID vaccine manufacturing. Almost all candidates that you might have gotten a vaccine from, like Pfizer, Moderna, Johnson & Johnson, all of them used our products. In short, we would say that like in the semiconductor and the high purity space, we offer currently the widest range of flow technologies, be it a flow measurement as well as flow control technologies in this market space. With that, let's move on to the presentation. So we are going to cover several topics, but to start with, we will be covering the role of the fluid flow measurement primarily in the Fabs, especially liquid space is what we are going to cover. In this discussions, we are not going to cover how the product or the technology works and its principle, but rather we will be looking at the nuances, pitfalls, and where it is to be applied, which is the right product for right applications. I try to maintain as vendor agnostic as possible, though there may be some references to our products in the discussion. The second topic that we'll be covering is the CMP slurry primarily, and we'll be discussing of the non-uniformity, how it impacts, and defectivity, tool improvements, throughput, etc. Wet processing would be the third space that we'll be discussing. And the fourth would be a technology selection framework, which basically we'll be comparing different flow technologies that are currently available and which one is better for which application, etc. And the fifth topic would be to discuss what are the advancements in the data connectivity between the flow measuring devices and the tools, so that you're not just merely looking at flow, but can you get more out of the product itself? And finally, we will just look at the what are the selection criteria for each of the products that you need to look into. With that, now let's go on to the area where what is at stake, and we'll just lay out the land before we go to the applications, etc. What is at stake? When you consider the advanced nodes like 3 nanometer and 2 nanometer, the fluid measurement is a yield variable. And also, if you look at the defectivity that might occur in the fab, one lot scrap event due to a defect can cost millions of dollars, and at least million plus, which itself eclipses the whole cost of the sensor for an annual budget for a fab. So that means it's so critical to select the right flow technology for right application. So now obviously the criteria for yield as well as the quality control on the wafer polishing, etc., is less than 1%, which is much more tighter. And as we advance to the newer nodes, such as 3 and 2 nanometer nodes, the number of steps that are involved in both wet processing as well as CMP tools are 10 times the previous generation. So that gives more important how do you select and how critical it is to upfront select the right product for right application. There are three fluid, especially in the liquid space, since we're going to discuss only liquid today. There are three fluid regimes that we are going to discuss. First is CMP slurries. Then next is wet chemistry and algae pure water. CMP slurry, there are a variety of slurries that are available, as you know, for different applications and different processes. Silica, ceria, aluminum, as well as tungsten slurries, etc. But the risk here is the agglomeration if you're not correctly designing the flow meter or flow controller, and if the path of the fluid is not well managed, the slurry can lead into agglomeration and settling risks, which can create wafer defects. So because of those reasons, the technologies such as paddle wheel or a vortex flow meter or a differential pressure flow meter or flow controllers are not really a choice. You have to go for an inline, but mostly non-obstructive type of a product. Wet chemistry, here the concern is that the chemistries are extremely aggressive in nature, extremely corrosive. Hydrofluoric acid, for example, hot SC1 and SC2 type of chemistries, formulations. and also very toxic TMAH type of developer chemistries, IPA, etc., are quite difficult to handle. Um, PTFE and PFA wetted parts are usually preferred. Particle shedding, contamination coming from the flow devices are extremely concerning. And if you have to maintain high purity there, uh, density and flow also matters in this space because you're really formulating chemistries, mixing different chemistries, etc. In case of ultra pure water, the level of contamination limits have drastically tightened. Instead of in the past, it used to be just parts per million and parts per billion. Now we are getting into parts per trillion type of deductions and limits established. So obviously, that's also a concern that we need to look into that. The flow measurement mistakes show up on the wafer, right? So we would wrongly diagnose the problem if it occurs. Often it could be the type of selection that we do it on the flow meters could lead into a defect. For example, measurement uncertainty can lead to control loop variations, which can lead into process turn uniformity and defectivity, etc. And hence a wrong diagnosis is possible. In case of CMP, flow drifts looks like a pad or a recipe drift, for example, but it often could be a flow controller, flow meter, could be the root cause. Wet clean example, density, again, like a concentration or density or pressure instabilities can cause different formulations not to maintain, and that could also create a problem. So we have to look at all these things while selecting the right product. So here, what are the application playbook in this case? There are five categories of chemistries that we have identified as a concern. So CMP slurry point of use, SC1, SC2 type of cleaning chemistries, as well as TMAH, ultra pure water, photoresistant developer chemistries, bulk chemical, and cabinets. In each of those categories, if you look at it, the objective to control is different, and what technologies that are applicable is also different. For CMP slurry, the stable dispense is critical, not only the flow rate as well as the flow volume. How stable it is during the flow rate is maintained for the dispense cycle. So non-invasive ultrasonic type of flow technology is usually preferred. In case of Malima, it's ultrasonic flow controller 7000 is often used in those applications. Chemistries like aggressive chemistries like SE1, SE2, and hydrofluoric acids are often the objective is how it is dosed, blended, and maintaining the concentration. In this case, both ultrasonic type of product as well as Coriolis mass flow based technologies are used. For the ultra pure water, contamination free is the criteria or control objective. So there, a non-obstructive flow path or a clamp-on devices are usually preferred. For photoresist or either a coated application, spin-on dielectric, etc., a low flow precision is required, extremely low dosage. The volumes could be in microliters, and in which case, low flow ultrasonic flow control flow meters can be applied. In bulk chemistry or chemical blending application, rangeability, uptime, maintenance reduction is obviously preferred. In this case, both ultrasonic and Coriolis technologies can be applied. With that, let's go into the application-specific case studies and areas of discussion. First, we'll take the slurry in CMP. CMP slurry really breaks all conventional flow measurement. You see, it has got abrasive particles. Obviously, it can lead to wear of different materials that touches that. Agglomeration, if there are any dead legs, the particles can agglomerate into a lump, and then it can cause scratches onto the wafer and hence defectivity. Shear sensitivity, because if you have any rotating parts in the device or any obstructions, that can create shear of the softer material, which is around the abrasive particle can come out and then can cause problems. So hence, generally the vortex flow meter or paddle wheel or a differential pressure type of a flow meters or flow controllers should be avoided. Uh, and obviously, those products also can have particle shedding risks. So there are two areas in the CMP slurry that we need to consider. One is a global loop where from the sub fab, the slurry is pumped to the fab level for different tool utilizations. In that case, keeping the slurry moving without any major cause of an obstruction um, and minimize that volume, how you maintain the stable pressure in that because you're supplying to a variety of tools. Those are the concerns. So in the flow control, for example, stable pressure control is critical in those applications. In point of use dispense applications in the tool itself, obviously inline flow meter without causing any obstruction is a preferred method. Very fast control because usually the dispense time is short, and if there is any excursions like overshot, undershoot could be a problem, and obviously non-uniformity risks are there. So in case of Malima, we have an ultrasonic flow controller that provides non-wetted PFA type wetted parts, and then no shear type of sensor technology is being used. So what are the technology fit for this area? So we kind of listed all technologies that are currently available for CMP slurry and which one is the best fit, which one is the poor fit. The first technology is PFA vortex flow meter. It's got a shedder bar, which actually obstructs the flow. And that is the technology. It uses the vortex shedding as the means to measure the flow. And the shedder bar would erode, and that would not be an ideal choice for slurry applications. In the past 3 decades before, paddle wheels were also used in those applications. If you look at older tools of 200 mm, 150 mm type of tools, CMP tools, you will find paddle wheels. Obviously, they have rotating parts, and it can drift, and it can jam, and it can shed particles, and hence it's really poor fit. The newer tools do not have them. Coriolis technology, while it is extremely ideal for high viscosity fluids, especially the slurries that have diamond slurry, for example, is a highly viscous fluid, in which case the Coriolis is perhaps the only fit. For other applications, it's because of the cost part of it, people prefer an ultrasonic over Coriolis. But wherever there is a high viscosity applications are there, Coriolis is a better fit for such applications. Differential pressure, while it can be suitable for the clean fluids, it is definitely not suitable for CMP slurry because you're crossing an obstruction in the flow path, and that can lead to clogging or abrasion and drift over time. So that would not be a fit. Ultrasonic is definitely a strong fit. There are two types of ultrasonic flow measuring technologies. One is clamp on. The other one is inline, though it is inline, the actual electronics and the sensing mechanism is externally mounted to the flow tube itself. So hence, pretty much no obstruction. It's very stable and very repeatable. It's extremely strong fit. If you notice, almost all CMP tools currently that's being manufactured, the first choice is ultrasonic, and second choice is Coriolis because of the high viscosity applications. There are 7 signs that one should look into that, whether the slurry flow meter or flow controller is lying. So this is critical. So I'm just giving it in a handout. Too many details, but I'll just highlight some of them. For example, signal noise increases after slurry switch or temperature changes. That's a sign, which can lead to flow meter issues. Yeah, and drift, whether it is drifting over a period of time, and not because of recipe change, that could be one of the flags. um, you know, an SPC flags removal rate while pressure and dispense look stable. So this could be one of the uh, signs as well. So these kind of excursions, one has to read through the um, possible failure points and checklists, and then identify where is the root cause, and then solve the issue. For the flow meter and flow controller side, as I mentioned, uh, PFA ultrasonic flow controller is the best choice. Why? Because it has got no wetted moving parts. Usually the transducer externally mounted to the PFA tubing, so pretty much zero contact with the fluid itself. Only PFA is in contact. No abrasive drift. Yeah, and you can place these flow meters or flow controllers closer to the point of use. And also very responsive and extremely repeatable in nature. Um, and wide range, it can be applied for a variety of slurries that are currently being used. And repeatability is one of the best features of this product. Uh, and a lot of tests have been done on the variety of tools that even over 1,000-hour period, the repeatability is very tight. So, hence this particular technology is in general the most commonly used and adopted technology for CMP slurries. And in our case, we have a model called LFC 7000 that does that. So this is just a highlight of how an excursion can occur in a CMP if you use, for example, the older technology products such as uh, either a differential pressure type or a paddle wheel technology. Over a period of time, you can see the non-uniformity rate will go higher, and that by degradation is happening. So that's an identity. This is not an exact number, but this, we are not highlighting. This is collected from the fab. So let's move on to the third section. We'll discuss about the wet chemistry or wet processing, and how the wet chemistry, uh, such as hydrofluoric acid, SC1 and SC2 type of chemistry formulations, TMAH, what type of measurement is the best suited for those applications. So here again, I kind of divided into 6 chemistries that are important, and then what are their uses, and what are the preferred wetted materials for those chemistries, and what are the best fit technology for that, and what are the pitfalls, and what are the concerns that you need to look into while selecting each one of those technologies. Dilute hydrofluoric acid, obviously, is extremely aggressive, as we know, and it's used in oxide etch and clean applications. PFA and PTFE, obviously, is the only choice. PFA more so than PTFE in the flow, especially constrained flow. Um, Ultrasonic and Coriolis flow meters and flow controllers can be applied here. Permeation is definitely a concern. So in case of appropriate thickness of the PFA tube, or um, areas where there can be a very thin layer of PFA rather than a thick, which can lead to permeation of the hydrofluoric acid gases through that, and that can lead into corrosion or unsafe environment. In which case, people sometimes use a purge fitting onto the devices to keep the pressure inside uh, the unit itself elevated, such that the permeation is somewhat limited and non-present. SC1 obviously has got ammonium hydroxide and hydrogen peroxide, either some independently or mixed, as well as sometimes elevated temperature as well. So there the particle concerns are there. PFA is pretty much the only choice. And both ultrasonic PFA as well as PFA ultrasonic flow meters or flow controllers as well as Coriolis flow meters can be used here. Bubble formation can be a concern because hydrogen peroxide under pressure, if you have any differential pressure devices or pressure drop creating elements in the flow path, that can lead to pressure drop, and the bubbles can get liberated. Bubbles are not good for certain technologies. There are a lot of advancements that have happened in ultrasonic flow meters that can overcome some limits of bubbles. Obviously, one has to take into consideration while installing these products. SC2 is for metal removal type of applications. PFA again, similar to the SC1, outgassing or bubble formation can be a concern. TMAH is a photolith developer application. PFA, P can be used, but mostly people use PFA in these applications. Best fit would be a PFA ultrasonic flow meter in this case. And concerns are toxicity and leak detection. So, it could be a very nasty chemistry. One has to look at the finding out any leak points are possible in the flow meters or flow controllers has to be looked into. IPA and solvents, usually di-margoni type of applications. In the past, people have used stainless steel, but PFA obviously is the preferred material at this point. So vapor pressure, etc., has to be created because it's non-conductive type of material. ESD concerns have to be also looked into such applications. Ultra pure water, obviously used for rinsing, dilution applications, rinsing of the wafers, so to speak. So here again, PFA is preferred. Clamp-on ultrasonic flow meter, because there's no obstruction, no contamination risk can be completely avoided. Again, no dead legs where then accumulation of particles can happen. So generally, ultrasonic, either inline or clamp-on is preferred here. So in the wet chemistry dosing, there are three different jobs often get confused, as I mentioned here. Flow verification, control, closed loop dispense, or more like concentration or density formulation or blending are the three areas that one has to look into. The main risk in the flow verification is the contamination. Obviously, if you have older equipments, older tools, and if you want to upgrade them to the newer flow technologies, then you can use clamp-on ultrasonic for those kind of applications. In closed loop, an integrated flow controller, repeatable dispense is critical, and here ultrasonic could be a good choice. For concentration mix ratio, where the mass and the density plays a role in mixing up different chemistries, especially SC1 and SC2 type of applications, that the Coriolis technologies is a better choice than ultrasonic and other technologies. So the right question is Coriolis versus ultrasonic. It is not Coriolis versus ultrasonic. It is where you're applying and what is the end purpose, and appropriately you apply the technologies. Let's look at Coriolis, especially in the formulation side or blending side. Because Coriolis is the only technology in the flow measuring world that measures flow directly, a mass flow is being measured. So mass is a conserved unit, unlike volumetric flow. So it is independent of the changes in viscosity, density, or temperature. So if you're using it for one chemistry and if you're applying it for different chemistries, you don't need to recalibrate the devices. And often these type of Coriolis mass flow meters provide density measurement. You can interpret that as a concentration. So it'll be helpful for blending different chemistries while formulating it. And it's extremely accurate, and PFA weighted parts are used in such applications. So the other product that wins in this application is the clamp-on ultrasonic flow meter. The advantage of this clamp-on ultrasonic flow meters is that it is fitted on externally to the tubing, so you're not breaking the tubing, so there's no leak points, there are no obstructions, no need to shut down if you're retrofitting older tools with the newer technologies such as clamp-ons. It's completely contamination free. As only the tube is of a concern here, and aggressive chemistries can be used, and then bulk delivery lines where the mass flow precision is secondary. You can use the clamp-ons. Clamp-ons are quite well used in sub-fab fluid chemistry blending as well as pumping applications. In case of Malima, we have a model called M3100 series. It's a clamp-on, non-intrusive, uses transit time technology. It can be applied to PFA or PVDF tubes. No wetted parts. It's available with 4020 and digital outputs. Widely used in variety of sizes like quarter inch, 3/8 inch, half inch, etc. So the caveat here is the clamp-on ultrasonic accuracy depends on the pipe geometry, fluid agnostic properties, and installation discipline. So for example, unlike the inline flow meters, which are made by the factory of a vendor, the calibration is done at the vendor location. But as in the clamp-on, the ownership of the installation of these devices onto the plumbing is managed by the customer, such as yourself. So there, I think the trade-off is that if you're not installing it correctly, obviously it can lead to errors in the device. So with that, keeping that in mind, the convenience of installation, clamp-on obviously stands out. So the questions to ask before selecting a meter. Okay, so will it work into specific design and applications? So that's what the criticality is, like whether don't go by the specification sheet or data sheet of a product. So whether it applies to my application and my location inside the tool where it is installed, whether it is tighter footprint, etc. In case of hydrofluoric acid, is every part wetted parts PFA. That's a very critical. And then what is the permeation? So thickness of the PFA tubes, or if you're looking at ultrasonic flow meter, where the piezo resistors are kept, which generates the ultrasonic sound, and whether the thickness between the PFA layer between the piezos and the fluid path, how thin it is. So those things can lead into permeation risks, and one is the lifetime of the product can come down, and second is it's a hazardous fluid. That's more concern, right? So in such applications, one could adapt, as I mentioned earlier, a purge. You can keep the product under elevated pressure such that the permeation is avoided in such cases. In case of a hot SC1 or SC2 type of chemistries, bubbles are extreme concern. So how you install a flow controller or a flow meter, where it is located in the plumbing can be important. For example, if you're installing a flow meter right after the control valve or a differential pressure causing element, often this high pressure hot chemistries will start to liberate gases or bubbles, and that can lead to a very inaccurate measurement, and it can also lead to drifts, etc. In case of TMAH developer, can the device be used for low accuracy without creating any dead volumes, because we don't want any hold up volume in TMAH applications. In IPA and solvent, vapor pressure, ESD is a critical. Right now, a lot of people are exploring using carbon filament type of PFA tubes to avoid ESD issues in the fab, and especially fluids that are such as IPA and solvents. The selection of the flow technology as well as the tubes are critical. Ultra pure water, can the measurement be done without adding any wetted surface? In this case, do I need to really cut it because already the ultra pure water is extremely pure, and do I need to add a device which can potentially contaminate? Um, so the clamp on could be a choice there, as we mentioned. So in technology selection framework, after discussing that, I think I tried to highlight the products as vendor agnostic as possible in this. So you can ask questions later on if there is any specific to any particular product or technology. A decision framework would be like, is the fluid abrasive or particle laden? So in such cases, PFA, ultrasonic, or non-intrusive like clamp-on ultrasonic could be a first choice. In other applications such as, do you need a mass flow for more accurate form of blending? Is concentration or density measurement critical? If that is important, obviously PFA, Coriolis mass flow meter or flow controller could be a choice. Is contamination free product is required, in which case either an inline PFA or a non-intrusive PFA like clamp-on can be applied. Low flow precision dosing in case of a coater application, photoresist dispense or spin-on dielectric type of applications, PFA ultrasonic flow meters that can measure flow accurately at 1/8 inch type of line sizes and microliter type of volume dispenses could be a choice. So no single technology is right for the whole fab. So there are a variety of technology that are available. So we need to match the technology to the chemistry as well as to the application, not to the vendor preference as I mentioned here. Specify under your actual conditions, not datasheet conditions. So for example, in some datasheets, you would have noticed that a flow controller will have a 10:1 turn down ratio, that is maximum to minimum control range. Whereas in your application, you might change the recipe so often, you may need to have a wider rangeability. In which case, instead of just looking at the data sheet of a product, you could interface with the vendor and then figure out a better rangeability, whether it is possible with the same device or what are the solutions available. So those discussions should happen instead of just selecting it from the data sheet. Lifetime and drift uh, uh, has to be considered as well. So lifetime, whether the products that the vendors are offering you, whether they have subjected the product to a lifetime study, how many million cycles of on and off for a controller is appropriate for you. For typically like 200K to 250K type of cycles will equate to roughly about 1 year of operation. So it varies from fab to fab, tool to tool. But such lifetime studies as the vendor done it. And also, what are the drift possibilities? Whether the product can drift over a period of time, do we have the data? So those kind of informations are very valid in selecting the right technology. Here I'm comparing three technologies and their trade-offs. Coriolis, ultrasonic and differential pressure type of flow technologies. Strengths, obviously, Coriolis measures mass flow directly, and it also measures density. You can interpret concentration of the fluid. An excellent low flow accuracy. The limitations are higher cost. Slurry, abrasive slurry can lead to tube erosion, which can lead into imprecision. So you have to select the Coriolis for the right application. High viscosity application is a great choice. Ultrasonic, this is the widely used technology in the market for chemistries as well as slurry. Non-intrusive is obviously very high strength for this product. Wide chemistry tolerances, long lifetime, no drift, wear, and very repeatable, which I have not listed here, extremely repeatable technology. Volumetric, obviously, it cannot measure mass, so it has to be fine-tuned for different chemistries. Uh, that's one limitation, but always it can be applied for a wide range of chemistries. In case of differential pressure technology, it's low cost, mature technology, very old technology. It's wide range, but extremely risk uh, in clogging because you're obstructing the flow, and the differential pressure causing element can erode over a period of time. And then since you are using two different pressures for measuring pressure flow, it can lead to drift. And then usually turn down is very low for this technology. You can only measure limited range for each size of the product, so to speak. The typical best fit for this application is bulk delivery, non-critical loops. Let's move on to the what are the demands for the high bandwidth memory, as well as advanced nodes, especially for the connectivity standpoint. Uh, just the flow meter measuring flow and outputting flow as one variable, is it sufficient? What are the other requirements? What changes in this advanced nodes? More tools per process module. Obviously, extremely higher number of data points are there, measurement points are there. More chemistry variants, obviously, the different mixers, different recipe changes occur frequently. Smaller batch sizes and higher mix. So that is also a critical point to note. And real-time data integration. For example, if you just measure flow and flow meter produces 4 to 20 milliampere or 0 to 10 volt output, just one variable. But nowadays, the advancements that are happening in the flow sensor technologies provides you more data about the health of the product, as well as additional variables like pressure and temperature in addition to the flow and density, for example. So such data cannot be transmitted by just two wires. So you need to have a digital communication using that same two wire, not by analog means. So predictive maintenance expectation also increases a lot with this concentration of so many products and process steps. So traditionally, people used 4 to 20 milliampere and 0 to 10 volts. Still, that's being used in with many tool manufacturers. In between, for now, a lot of people still offer Modbus and other digital communication protocols from the devices to the tool, enables easy integration, etc. But more advanced industrial communication protocols are now being adopted. Vendors also provide, as well as the OEMs also try to integrate these advanced. EtherCAT is gaining traction in a variety of tools. Ethernet IP could also be used. And there are other communication protocols are also being offered. So the advantage, as I told you, is that it gives you more data, not just the flow. And that's very critical in these kind of areas. Right? So how do you specify and qualify in considering all these criteria? What questions we need to ask and what mistakes should we avoid? So I kind of listed 6 things which I think it's critical takeaway in this. One is fluid measurement is a yield variable at advanced nodes, and we should treat it that way. It's not just a flow meter, it's costing $500. Is it worth it? But if you've selected a defective technology there, and it can lead into even one excursion, as I pointed out earlier in the presentation, one lot of wafer defect can lead into $1 million plus in the cost for finding the root cause and then fixing it. So let's select the right product for right application upfront rather than just looking at data sheets and the price of the product. And no single technology serves the whole fab. That I think we should understand. While ultrasonic flow technology is widely used, there are other technologies can be utilized for different application segments. For example, chemical blending applications, uh, uh, the Coriolis technology could be adapted because it provides more information such as density and mass, temperature and pressure, etc., by single device. So we should match the technology to the chemistry as well as the application. For CMP slurry, lifetime and drift dominate as we looked at it. So what sort of studies the vendor has done it um, to validate the lifetime of the product? Because one failure in the tool means that you have to, the maintenance engineer has to gown up and then get into the tool. You have to shut down the tool, take it out, and it's a quite an expensive uh, exercise. So a very reliable product is extremely important. Um, and obviously non-intrusive measurement wins some applications, but not in all cases. Coriolis, as I told you, mass and density matters. Ultrasonic, when contamination free, matters. Specify and test under your condition. So if you're an OEM or end user, the test data for actual application is more critical than just a data sheet conditions. That is very important. Uh, for example, we have done several studies with several customers on actual fluid conditions, either at customer location or at our factory. So EtherCAT or any advanced digital communication protocols are really critical these days because you want to pack more data on and communicate to the tool, be it a health or additional parameters such as density, temperature, or fluid concentration, etc., can be done. So with that, I'm concluding the presentation, and I'm just going to leave the session for any questions or any discussions that you may have.
All right. Well, thank you, Jay. That was a very good presentation. We appreciate that. And so we have entered the Q&A portion of the webinar. And as a quick reminder, you can ask a question easily. Just use the chat function on the right-hand side of your screen there. So we do have some questions already. Let's see. Space constraints inside our wet clean skids and chemical blend cabinets make straight pipe runs practically impossible to design around. When retrofitting tools are designing compact UHP skids with Melima's PFA, Coriolis, or ultrasonic meters, how heavily do upstream and downstream straight pipe runs impact measurement accuracy?
So if you're considering ultrasonic flow controllers or Coriolis flow controllers, let me take Coriolis first. Coriolis flow meters generally do not require upstream and downstream pipes, straight runs, so to speak, unlike the vortex flow meter or a differential pressure type of flow technologies. So that wins hands down. In case of an ultrasonic flow meters, while a straight tube flow meter may require upstream and downstream straight pipe runs, the flow controllers uses Z or U tube type of flow sensor, in which case the measurement section itself is straight and it is contained. So you don't need external straight runs before and after the flow meter. I hope it answers.
Yeah, it does. Okay, thank you. Another question here, and that is, which technology provides the lowest flow control for water, say nanoliters per minute?
I would say at the moment, ultrasonic is the right technology for those applications, because ultrasonic flow meters are available in 1/8 inch type of sizes. And if it is a short dispense duration as well as volume, uh, ultrasonic flow meters are currently being used in coating applications, like, for example, photoresist dispense or spin on dielectric or spin on glass type of media, that usually you squirt a small dose of such chemistries onto a wafer that's spinning at extremely high RPM, and the chemistry spreads out and coats it. And in such applications, the ultrasonic flow meters generally wins hands down. One, it's available in such small sizes. Second is usually the number of data points an ultrasonic flow meter can measure per second is much greater than other technologies. For example, an ultrasonic flow meter typically measures anywhere from 200 to 300 data points per second. So if you're using it for a small dispense, a micro dispense, it's a short duration of time. So your data that you need to get out of the sensor flow data to characterize the flow itself is critical. Other technologies like differential pressure or a paddle wheel, um, or a vortex, for example, they're slower in response compared to ultrasonic. So ultrasonic wins hands down in those applications.
Yeah. Okay, thank you. Let's see, in our CMP slurry loops, microbubbles and outgassing are constant battles that cause traditional meters to stall or lose signal entirely. From an engineering standpoint, how does Malima's digital signal processing allow your UHP Coriolis meters to maintain a continuous, stable mass flow measurement even when gas void fractions spike?
Yeah, so that without dwelling mostly into proprietary information, but what I would say is that the digital processing technology, both in ultrasonic as well as Coriolis, allows us to uh, characterize the signal that's coming out of the sensor during such bubble conditions and how to avoid and hold the old known value for a short duration of time. That's one way of doing it. In case of Coriolis flow controllers, the technology itself allows us to, because you're measuring mass, and mass of a bubble or liquid, it's still a mass is mass. So you're not really interpreting as a volume and then incorrectly measuring when the bubble is present, for example. So using a mass flow for such bubbly conditions as a technology itself is a preferred approach. Uh, and then you have to orient these sensors uh, in such a way that bubbles are not accumulated and trapped in certain locations, thereby preventing the flow measurement to happen. So you can, for example, in ultrasonic flow controllers or flow meters, we use Z-shaped sensors. You can orient the Z shape in like 45-degree angle, for example, thereby uh, avoiding any trapped zones to accumulate, the bubbles to accumulate, for example.
Okay. Here's a tough one. With sub 2 nanometer nodes requiring aggressive chemistry at elevated temperatures, exotic metals are no longer an option in the wetted path due to trace contamination risks. What were the biggest mechanical and calibration challenges your team had to overcome when designing all PFA wetted paths for Coriolis vibrating tubes to minimize zero drift over long-term thermal cycles?
Yeah. So when you're characterizing a device for high temperature, of course, you have to look at the design consideration of how do you um, select the materials, etc. That's one concern. The second concern is the how you test it in the labs uh, in the vendor location before the product gets shipped for use in certain location in customer location, for example. So you often the vendor labs may not have the equipments to deal with such high temperature chemistries, for example, because they're all you need to get certain compliance before we can do it. So we might be using a different chemistry for characterizing the sensor, maybe an oil or anything like that, and then derive uh, a factor or a characterized data. And in production, we use clean chemistries for calibrating the device. For the development time, you use different chemistries that can mimic those uh, characteristics of the chemistries that are used by the customers uh, to increase the temperature, and thereby it can be tested for long duration of time without stopping it, and collect the data such as repeatability, lifetime, etc., and then use that information transported to the chemistries that are used by the customer, for example.
Okay, thank you. And I think this is the last question. In single wafer track or spin coater dosing applications, our valve open and close cycles are ultra short. How do Malima's integrated liquid flow controllers manage to stabilize and prevent flow or pressure overshoot during these rapid sub-second transient windows?
Uh, so there are multiple ways that's been done. One is that you could, if it is a flow controller, you could um, freeze the control of the valve when the dosage command from the tool um, is stops, for example. And then when it comes to the next cycle, it's the control valve is already in a previously known position, and thereby you can reduce an overshoot, for example, when the new command is received. So that's one approach. Second approach is that we could use a fuzzy logic and characterize at what pressures roughly and what uh, duration of dispenses, what is the position of the valve has to be. And then you can program the device. It's kind of a more like a anticipatory type of control. So if it will anticipate um, the control should reach this set point fairly quickly. So we use a kind of a fuzzy logic to achieve that kind of a scenario.
Okay, perfect. Well, those were the questions. So thank you. And any final comments? What's the best way to work with Malima?
Yeah. So in the handout, I have given uh, the contact information for myself, but you can always reach out to the main website, and you can request either for uh, an appointment with our application engineering team to validate your application or work out a best fit. We can even provide samples to do a evaluation at your fabs or an equipment, for example. And those kind of conversations can happen with our application engineers, and it can be they can be reached out either through me or through data provided in our contact information provided in our website.
Okay. All right. Well, we have almost reached the top of the hour, so perfect timing. Thank you, Jay. Thank you, audience, for joining us. And don't forget to download the presentation. And with that, we'll conclude, and we look forward to future webinars.
And thank you, everyone, for joining, and thank you, Pete, for hosting us. Yeah, thanks a lot.
All right. Thank you. Bye.
Bye.